So before I move on to the software considerations and requirements, I'd like to just highlight some of the key challenges that we face in implementing full-scale quantum networks. These challenges are, it's not as if they're not present in the smaller scale networks and the kind of pilot and trial test beds, but as we really scale up the complexity of the system, we're adding new pieces of hardware and longer distances, etc. These challenges really play a key role, and they're bigger and bigger hurdles to overcome. So we all know quantum states are very fragile, especially in these first generation protocols where we're encoding in single photons. So they're very fragile. Again, we spoke about photon loss and noise. So those are key challenges in quantum networks. As you scale to a full-scale deployment, we're going to have pieces of hardware from many different vendors, presumably, each with different ways of doing things. So being able to work with these different products from different vendors is a key challenge. Of course, there are always going to be manufacturing defects in the components we integrate. So dealing with that. Another factor is polarization drift. So if we're encoding our quantum information and polarization in photons, this polarization can sort of drift as it's traversing a channel, and this could be due to temperature fluctuations, atmospheric considerations, stretching, vibration, so all environmental factors that could affect the encoding of our quantum state. So we need to compensate for those effects. Again, the timing and synchronization plays a key role and is more important as you scale up. So thinking about the timing of all the operations that are going on in all these nodes, thinking about the timing of messaging and classical messages traversing the network, thinking about latency of software. These are all things to take into account to coordinate this complex dance. Resource management is a key theme here that I'll return to as I continue, but the general point is that this network is growing in complexity. There are more pieces of hardware, more quantum resources, and presumably more users on the network and more applications being run. So we need to manage all of these resources effectively and optimally. As our networks scale in complexity, we're supporting different kinds of topologies. Traffic engineering will play a key role. And this is similar to what we saw with the evolution of the classical internet as well. So thinking about dynamic routing, thinking about multi-tenancy, and being able to dynamically route around bad parts of the network or oversaturated, overused parts of the network. So traffic engineering also will apply to quantum networks. And generally, there's this theme of maintaining reliability as you scale in complexity, right? Things will go wrong, things will perform under par or not as you expect, things will go out of sync. So as you fix those problems, as you integrate new devices into the network or take devices down for upgrades or maintenance, you don't want to take the whole network down, right? You want to maintain that reliability and operational capability of the network. So all these challenges play a bigger role in full-scale deployed networks relative to the smaller pilot and trial networks. That really gives way to this new paradigm of software-defined quantum networking. So let's talk about these software requirements and considerations. So starting at the top, we're going to need a way to actually use this network, right? We're going to need a platform where users, either internally or externally, can use the network, can schedule experiments and applications, define how they want to configure the network, what performance metrics does their application need to meet, so defining quality of service parameters, things like that. This is the touch point of the quantum network, so we're going to need that application layer. Not only for the users, but also for the network operators, which is really important. And this, for thinking about managing the user access, potentially some users may have priority than others, thinking about all the business considerations, accounting, billing, etc. But also general network management, so doing upgrades, monitoring, things like that. So having that operator interface is key. At the management layer, this kind of centralized controller, again, drawing analogies to classical networks as well, software-defined networking concept. So at the management layer, this controller has a global view of what's going on in the network. So monitoring network health, network performance in real time is extremely important. But also, conducting network level optimizations and protocols. So optimizing resources, how do we manage all of these resources for all of the service requests that are coming in from that application layer, all the users that want to use the network. We need to somehow, orchestrate this network to meet those needs. Also, so some security baked in here, right? So detecting if someone's trying to mess with the network, if there's an eavesdropper in, so that this is done at sort of the management layer in coordination with the lower layers as well. And then, as I said before, as you scale up from local area to metro area to wide area networks and to this full scale deployment, thinking about traffic engineering, thinking about dynamic routing. These are all lessons we've learned from classical networks. Now at the lower layers, this is really the meat and potatoes of the quantum network. This is where things get done and entanglement is being generated and purified and swapped around, and we can mitigate errors and potentially have quantum teleportation as a subroutine. So these are the quantum protocols that sit right above the quantum hardware. But additionally, not just the quantum protocols, but the classical protocols necessary and the classical software necessary for enabling these protocols. So clock synchronization, the timing systems we need, calibration to make sure we're accurately compensating for errors and the devices are actually performing as intended. Another key part is this last one here about a hardware agnostic interface. And as we scale up our network and integrate new pieces of hardware from different vendors, we need to make sure we can work with all of those products and vendors, and ensuring that these devices play nice with each other and actually interoperate. So having this hardware abstraction layer is a key role of the lower levels.